To finish up this chapter, let's just work some additional practice problems to make sure you're comfortable with the content we've covered. Example 1. At what temperature is the following process spontaneous at 1 atmosphere? Br2 liquid going to Br2 gas. In other words, what's the normal boiling point of Br2 liquid? See, the thing is, I don't have to say this question in words. I could just ask you the top one, and then students shut down because they're like, what? What does that mean? It really means that if this process is spontaneous, I'm looking for the boiling point because I'm going from a gas phase to a liquid phase. That's something you need to get or delve from just reading the question. Another thing I want you to think about is, what does spontaneous mean? Spontaneous means that delta G is less than 0. It also means the reaction will go on its own. So at what point are you going to actually boil bromine? Well, you're missing some things here, right? Some values. When is it going to boil? What's the delta H vaporization? What's going to happen for delta S? Is it favorable to boil this or not favorable? What we're going to do is we're going to use this equation, delta G equals delta H minus T delta S. But I'm missing some pieces here. I'm trying to find temperature, so I'm trying to find T. I know delta G has to be less than 0, so I know that, but what about H and S? Well, where can we find those? We can find those values in the back of your book. What you need to remember is that the delta H value here, you can look this up, delta H is 31.0 kilojoules per mole for this process. How do I know that? Because I look up the delta H for this, I look up the delta H for this, and it's products minus reactants. I can also look up the delta S value. Delta S is going to be 93.0 joules per Kelvin. How do I know that? Again, I can look it up the same way I looked up I can look up S the same way I looked up delta H, and I can calculate it, products minus reactants. Now I look at these values and I say, okay, well, what if it's always spontaneous? No, it's not always spontaneous. I know that bromine's not always going to go to a vapor phase, or we'd never have a liquid ever, right? If you look at delta H here, delta H is a positive value, meaning that this does not favor vaporization. Think about delta S. Delta S is a positive value, and does that make sense? Yeah, it makes sense. It favors disorder because it's going from a liquid phase to a gas phase, which is more disordered. It also makes sense that my delta H value is positive because it's going to take energy to break up the intermolecular forces holding these molecules together to get them into the vapor phase. Do you have to do all this just to do the question? No, you don't. You have to figure out the values, yes, but you don't have to understand the rest of the stuff. But it's good to understand it because you should understand what the question is really asking. This is an endothermic process. Remember, at the boiling point, what's going to happen? Boiling point is an equilibrium. At the boiling point, it is at an equilibrium between the liquid and gas phase. If I tip below that boiling point, it's going to be in the liquid phase. If I tip above the boiling point, it's going to go to the gas phase for the bulk of the molecules. At equilibrium, at boiling point, it is at equilibrium. Delta G is equal to 0 at equilibrium. So, delta G is equal to 0, is equal to 31.0 kilojoules. When you write it for the reaction, it's just kilojoules. For delta H minus T times delta S, but I need this in kilojoules because I've got the rest in kilojoules, 0.0930 and that's joules per Kelvin. Go ahead and solve that through, and we get a temperature of 333 K. What does that really mean? What does this mean to me? It means that if the temperature is greater than 333 K, entropy controls the system, and it is a spontaneous process. If the temperature is less than 333 K, there should be an extra 3 there. Your enthalpy controls the system, and it is not spontaneous. The reaction CCl4 gas going to C carbon or carbon graphite plus 2 moles of Cl2 gas has a delta H value of positive 95.7 kilojoules and a delta S value of positive 142.2 joules per Kelvin. Calculate the minimum temperature for this reaction to be spontaneous. Same thought process we just talked through, so I'll go through it faster this time. We know delta G is equal to delta H minus T delta S, and we know delta G must be less than 0 for it to be spontaneous. Plug in our values. Delta H is 95.7 kilojoules minus the temperature we're trying to solve for, and S, I need to convert this to kilojoules or convert delta H to joules, whichever one you prefer to do. I prefer to convert this to kilojoules. 0.1422 kilojoules per Kelvin. That is less than 0. Go ahead and move. You're going to have negative T times 0.1422 kilojoules per Kelvin less than negative 95.7 kilojoules. I'm trying to isolate that T. Divide through by negative 0.1422 kilojoules per K. Cancels out my kilojoules. This Kelvin is in the denominator, so it's now a numerator. I get temperature here. The math here will be 673 K. But remember, when you divide, when you have an equality sign like this and you divide by a negative number, you have to flip the equality around. So that means you have to flip it this direction. The temperature will be greater than 673 K. Calculate delta S at 298 K for the reaction. 2 moles of NiS plus 3 moles of O2 give me 2 moles of SO2 and 2 moles of NiO. Look through the table and find all your pieces. So NiS, make sure it's in the solid phase. Let's see, O2 gas for S actually has a value. I just don't see it on the table, so I'll have to give you that one separately. I might have forgot to put that on the table, and I apologize. SO2 gas and NiO, and that is a solid phase. So NiS, and we are looking for S specifically here. So this is 53.0 joules per mole K. O, because I somehow forgot to copy that part in the table, and I apologize. That is 205.0 joules per mole K. Remember, for elements in their most stable form, so even including like diatomics at that point, they're 0 for H and delta H, delta G, but they're not 0 for S. Not at 25 degrees C. For SO2, we've got 248.2 joules per mole K. And for NiO, we've got 37.99 joules per mole K. So this is what I call the products minus reactants reaction. But don't forget to factor in moles. Delta S, 2 moles, my SO2, times 248.2 joules per mole K plus 2 moles nickel 2 oxide, 37.99 joules per mole K, and I'm going to run out of room. So minus 2 moles NiS, 53.0 joules per mole K, plus 3 moles of O2 times 205.0 joules per mole K. Do all the math. You get a delta S. I'm so used to calculating delta H. Delta S value here, negative 148.62 joules per Kelvin. But if I look at sig figs here, let's see, that has 4, 4, 3, 4, and that's accurate to the first, everything's accurate to the first decimal place. This will be negative 148.6 joules per Kelvin. Predict the conditions in which the following reaction will be spontaneous. FX6 going to SF liquid. Well, let's think about this. I know spontaneous means delta G is less than 0. I know delta G is equal to delta H minus T delta S. So is this reaction always spontaneous? No. Why? Well, I'm going from gas to a liquid phase. So delta S is a negative number. It's not favorable. That would be negative here. Negative times negative is positive. Depending on what delta H is, that could overpower delta G. So it is not always spontaneous. Is it always non-spontaneous? Well, is it ever possible to be at a different temperature? Let's check. Delta S is negative. If delta H is positive, delta G would be positive and it would be never spontaneous. But what if delta H was in fact negative? If delta H was negative, that would give me a negative, positive here. Overall, if delta H was large enough, so if we keep the temperature low enough to not overpower delta H. Is that possible? Well, are we sure delta H is going to be positive? We don't have values, right? Solid phase, liquid phase, gas phase. Delta H. Going from the gas phase to the liquid phase. Delta H is a negative number. So it's not spontaneous. It's not enough information. There is enough information. Delta H is in fact negative. Delta S is also negative. So this will be valid at low temperatures. Low temperatures so that the temperature times your entropy value are not powerful enough to overcome your delta S. What we do is we call this it's thermodynamically controlled. It's enthalpy driven reaction. When 1 mole of liquid water is frozen in a freezer at negative 10 degrees C, what are the relative values of delta S of the system and delta S of the surroundings? Is the reaction spontaneous? Let's see. Think about frozen water. If I freeze water at negative 10 degrees C, this is spontaneous. It's going to happen, right? We know logically that if I put water in a freezer, it's going to freeze. But my delta S in my system is going to be less than 0. It's going to be a negative value because it's a more ordered system. I'm going from water, liquid, to water, solid. Delta S is not happy. It's a negative value. I know delta S of my system is going to be greater than 0. So it cuts off the first 3 options. Is it spontaneous for my surroundings or non-spontaneous? It is spontaneous because I know this will absolutely freeze. In this next problem, we're going to do it's one example, but we're going to do 3 different parts to it, 1, 2, and 3 for it. So the Haber process itself is a world-known process for the production of ammonia. You take a mole of nitrogen gas, react it with 3 moles of hydrogen gas, and you produce 2 moles of NH3, or ammonia gas, but this does exist as an equilibrium system. I want you to estimate the equilibrium constant and position of the equilibrium constant for the following reaction, or the reaction above, at 427 degrees C. 427 degrees C is the same as 700 Kelvin. How am I going to do that? Well, I need values first. Delta H, 2 moles, NH3. You can look up these values in your book. Minus 45.9 kilojoules per mole. Minus 1 mole N2 times 0 kilojoules per mole plus 3 mole H2 times 0 kilojoules per mole. Again, those are 0 because they're in their most stable state. So I find the delta H value here to be negative 91.8 kilojoules. I'm going to follow the same process for delta S. Delta S, I've got 2 moles of NH3. The delta S value of NH3 gas is 192.8 joules per mole K. One mole of N2 gas. There's an actual value here, 191.6 kilojoules per mole, because again, everything has an entropy unless it's at absolute 0, and we are not at absolute 0. 3 mole H2 times 130.7 kilojoules per mole K. Negative 198.1 joules per Kelvin. Now I can use that information to find delta G. Delta G is equal to delta H minus T delta S. Delta H is negative 91.8 kilojoules per mole, or you could put everything in joules. I don't care which way you do. I wrote in my notes it's everything in joules though. 91800 joules. Minus T, 700K, times delta S, which is negative 198.1 joules per Kelvin. And that's why I had to convert my delta H to joules, because this is in joules. Delta G here, I calculate out to be a positive 46870 joules. Now I have delta G. So I've used delta G equals delta H minus T delta S, but I really want the equilibrium constant. I know that I also have delta G naught is equal to negative RT ln of K. So delta G naught, negative RT ln of K. We just calculated delta G naught because it was from the standard conditions. Equals 46870 joules. And this is equal to negative 8.314 joules per mole K times temperature 700 K times natural log of K. And I know we theoretically cancel out joules here, but I'm going to put the joules per mole back here because it does cancel out properly with R that way. Solve mathematically for this. You're going to find ln of K is equal to negative 8.05 e to the negative 8.05. To undo that log gives me 3.18 times 10 to the minus 4th. This is equal to K. K is a lot less than 1. Therefore, this is reactant favored. But again, I was trying to find the equilibrium constant. I know this equation for equilibrium constant. I was able to calculate my equilibrium constant here. But in order to calculate this, I really had to find delta G. I can use this, sorry, wrong highlight, this equation to find delta G, but I need delta H and delta S under standard conditions. So I had to look up all those values and calculate that first. Now, what if I said calculate delta G at standard temperature for a reaction mixture that consists of 1 mole or 1 atmosphere of N2, 3 atmospheres of H2, and 0.5 atmospheres of NH3? This is under non-standard conditions. I know delta G is equal to delta G naught, which I've already calculated, minus RT ln of Q. I know Q is my reaction coefficient, so the pressure of NH3, quantity squared, divided by the pressure of N2 times the pressure of H2, quantity cubed. My pressure of NH3 is 0.50 atmospheres, quantity squared. Remember, on reaction coefficients, we can drop your units. 1.0 atmospheres and 3.0 atmosphere cubed. This gives me a Q value of 9.26. Sig figs are here. I'm just going to keep one extra sig fig for right now so that I don't round wrong. Times 10 to the minus third. Plug that into your equation. Delta G is equal. Tells me my delta G value right here. Negative 33.34 kilojoules per mole minus 8.314 joules per mole K. I need those in the same units, and I always forget to do that. 8.314 times 10 to the minus third kilojoules per mole K. I only noticed it because I looked at the kilojoules over there, and units weren't going to work out. Be careful of that. I forget about that all the time, for R specifically. Natural log 9.2, that's where my sig figs are, 6 times 10 to the minus 3. Delta G under these conditions is negative 44.9 kilojoules, which we round to negative 45 kilojoules. And the last example, delta G at 298 K for this reaction is negative 33.3 kilojoules per mole. What is the value of delta G at 298 K for a reaction mixture that consists of 1.9 atmosphere N2, 1.6 atmospheres H2, and 0.65 atmosphere of NH3? Same process we just followed. Q is equal to the partial pressure of NH3 squared divided by the partial pressure of N2 times the pressure of H2 cubed, 0.65 quantity squared, divided by 1.92 times 1.6 quantity cubed, 5.4 times 10 to the minus 2. Delta G is equal to delta G naught minus RT ln of Q equals negative 33.3 kilojoules per mole minus 8.314 times 10 to the minus third joules per mole K. Your temperature is 298 K. And natural log 5.4 times 10 to the minus 2. Delta G is negative 41 kilojoules per mole. Okay, you guys are ready. You're done with this chapter.